In the comments on my last video, someone told me their father was on the Mosquito design team at Salisbury Hall, and they wanted to know why de Havilland chose that strange wing shape. Then came 5 words that stopped me. Sadly, he died 15 years ago. The person who asked the question was also the person who could have answered it. Their father had been in the rooms where the decisions were made, had seen the drawings take shape under R.E. Bishop's supervision through the spring and summer of 1940. 4 separate commenters on that video revealed direct family connections to de Havilland workers, fathers, grandfathers, uncles who built the wooden wonder with their hands. All dead now. The knowledge they carried about why certain shapes were chosen died with them. The de Havilland Aircraft Museum, which houses the original prototype W4050 at the very location where it was built, states plainly, "Despite all our research, we've not been able to definitively prove why the Mosquito had its triangular wings." That's not hedging. That's the institution with the most access to surviving materials admitting the documentation doesn't exist. What follows is reconstruction, engineering logic that makes sense of the shape, pieced together from what we know about wood, about glue, about the practical realities of building an aeroplane from trees during the Battle of Britain. The Mosquito wing has a straight leading edge. Most aircraft of that era had tapered leading edges, wings that narrowed smoothly from root to tip on both the front and back. The Supermarine Spitfire, the Hawker Hurricane, the Bristol Blenheim, all featured conventional double taper designs. The Mosquito only tapers on the trailing edge. The front stays ruler straight from root to tip. Combined with how the wing sits on the fuselage, this creates what appears to be a forward swept look, almost triangular. The wing spars tell us where to start. Both principal spars were of ply box construction, 0.25-inch birch plywood webs with laminated spruce flanges. Over the inner portion of the spars, ash reinforcing members were glued and screwed to the bottom flange. The top skin consisted of 2 sheets of ply, with spruce members running span-wise between them, forming a cellular structure. The whole wing was screwed, glued and pinned, then covered with fabric over the plywood. The materials were precisely specified. Sitka spruce for the flanges, one of the strongest softwoods available, with an excellent strength-to-weight ratio. Yellow birch for plywood components. Canadian birch and Australian coachwood for specific applications. Douglas fir where additional strength was needed. The complete list of woods used in Mosquito construction reads like a global timber inventory. Ash, balsa, beech, birch, coachwood, Douglas fir, spruce and walnut. Each selected for specific structural properties, tested to specific moisture conditions. 15% moisture content was standard, and stress durations. The wing spars extended from wingtip to wingtip with no central joint. That's a continuous run of laminated wood, over 50 feet of structural member that had to resist the bending forces of flight, the weight of Rolls-Royce Merlin engines, the stress of combat manoeuvring. The rear spar, in particular, was one of the most complex units to laminate and finish machining after bonding and curing. Due to the combination of dihedral, the slight upward angle of the wings, and the sweep of the trailing edges, this spar required exceptional precision in manufacture. The casein glue holding it together required specific clamping pressures during assembly. For softwoods like spruce, the required pressure ranged from 10 to 150 pounds per square inch. For hardwoods like ash and birch, up to 200 pounds per square inch. Steel band clamps tightened by turnbuckles compressed and formed the inner plywood skin, the balsa filling and the outer skin over mahogany moulds. The assembly process itself was an exercise in controlled compression. Every joint pressed together with measured force before the casein cured. Wood glue joints have a peculiar vulnerability that any craftsman in 1940 would have understood instinctively. When you try to slip one glued piece past another, shearing motion, the solid glue filling the nooks and crannies of the wood surface resists very well. The mechanical interlocking created when glue fills surface roughness provides strong shear resistance. Chemical bonding between the adhesive and wood fibers adds to this strength. But when you try to pull a glued joint apart, putting it under tension, those mechanical bonds are weaker. The small nooks and crannies that hold firm against sliding motion fail more easily when pulled straight apart. Shear loads are survivable. Pure tension is the enemy. In flight, a wing bends upward under lift. The upper surface goes into compression, material pushed together. The lower surface goes into tension, pulled apart. If your wing structure is made of laminated wood held together by casein glue, you want to design the structure so that the loads on your glue joints favour the directions where glue performs best. R.E. Bishop led the design team that conceived this structure. Bishop had been raised in the de Havilland tradition, coming up under Arthur Hagg, who was primarily a boat builder before he was an aircraft designer. That lineage matters enormously. Wooden boat construction and wooden aircraft construction share deep principles. Stressed skin monocoque design, the management of compound curves, the behaviour of laminated wood under load. The story of Bishop's inspiration captures something of how design thinking worked in that era. He reportedly conceived the idea of the Mosquito when he saw a stuffed pike in a glass case and penciled a similar streamlined outline. Visual intuition, analog reasoning, the shape of a predatory fish becoming the shape of a fuselage that would hunt German bombers. Bishop's background wasn't conventional aeronautical training filtered through aluminium and rivets. It was craft knowledge applied to flight. The same instincts that told a boat builder how to laminate a hull for strength told an aircraft designer how to build a wing that would survive the stresses of 400 miles per hour flight. The design work happened in secrecy, away from the main Hatfield works. In April 1940, the design team relocated to Salisbury Hall, a remote Tudor manor with a moat, chosen specifically because it could be hidden from German reconnaissance. Craftsmen worked through the spring and summer of 1940 in great secrecy, gradually shaping what would become prototype W4050 in a small hangar disguised as a barn on the other side of the moat. The work continued through the Battle of Britain. While Spitfires and Hurricanes fought overhead, the team at Salisbury Hall bent plywood, laminated spruce, mixed casein glue. Interruptions to production due to air raid warnings cost nearly a third of de Havilland's factory time at the main Hatfield works during that summer. But Salisbury Hall was remote enough, hidden enough, that the prototype took shape largely undisturbed. By November 3, 1940, the prototype was ready to move from Salisbury Hall to Hatfield for flight testing. There was a problem. The wing chord was too wide for the gate. The aircraft that had been designed to slip through enemy defences couldn't fit through the entrance to its own birthplace. They found another way out. 22 days later, on November 25, 1940, Geoffrey de Havilland Jr., son of the company founder, chief test pilot, flew W4050 for the first time. A 30-minute flight. Only 11 months had passed since the start of design work. The aircraft that would become one of the fastest operational aircraft of the war had taken shape in a barn behind a moat while Britain fought for survival. The prototype went to Boscombe Down for evaluation. During handling tests, evaluators assessed the Mosquito's flight characteristics. The aircraft had several handling idiosyncrasies. The official pilot's notes for the trainer variant were later criticised as wholly inadequate, failing to properly describe the aircraft's behaviours. On one test flight, Ronald Bishop himself went aloft, watching his creation perform. Modern pilots who fly the surviving airworthy Mosquitos offer a perspective the original test pilots couldn't have had. Comparison across decades of aviation development. One contemporary assessment notes that, given its reputation for manoeuvrability, to me it feels slightly heavier in roll than I expected. The legendary nimbleness, it seems, was relative to its contemporaries rather than absolute. The engines sit in nacelles that protrude forward of the wing's leading edge, housed in the leading edge section of the inboard wing. The nacelles extend rearward past the trailing edge, with the flaps locked in the up position in those areas. From a pure physics standpoint, concentrating mass closer to the aircraft's centerline reduces roll inertia, the resistance to rolling motion. Tests with ground vehicles have shown roughly 20% reduction in moment of inertia when mass is positioned at the center rather than at the extremes. Whether de Havilland designed the engine placement specifically for roll handling benefits can't be established from surviving records. The engine position served multiple requirements simultaneously: center of gravity management, propeller clearance, nacelle aerodynamics, cooling airflow. Any roll rate benefits may have been a happy coincidence rather than deliberate design intent. The pattern we encounter repeatedly with the Mosquito is that the engineering decisions produced cascading positive effects, but the explicit reasoning was rarely documented. The cross-lamination technique used in the Mosquito's construction complicates any simple story about straight grain. The woods were laminated in different directions to compensate for wood's anisotropic properties, its tendency to behave differently depending on grain orientation. In tail structures, grain was set to run at an angle to counteract twisting motion. This was deliberate engineering to distribute stress across multiple grain orientations, not adherence to a simple straight grain only rule. The relationship between internal spar construction and external wing planform is therefore not as direct as the simplest version suggests. The straight leading edge may have simplified certain manufacturing processes. Straight edges are easier to produce consistently than curves, which mattered when you're building thousands of aircraft under wartime pressure. The wing shape emerged from a negotiation between aerodynamic requirements, structural constraints, and manufacturing practicality. Geoffrey de Havilland himself understood the production advantages of wood construction. He argued that in wartime, shortages of aluminium and steel would occur, but supplies of wood-based products were adequate. Although wood was inferior to metal in tension, the strength-to-weight ratio of wood equaled or exceeded light alloys and steel in many applications. Metal industries would be overstretched. Woodworkers and wood materials could be sourced more easily. The timber construction allowed components to be subcontracted to firms with woodworking expertise. Local companies, identified as having manufactured wooden parts for the Mosquito, include Dancer and Hearn, E. Gomm, Stiles and Mealing, Heathland Furniture, and Walter Lawrence. F. Wrighton and Sons emerged as perhaps the most significant UK subcontractor for Mosquito timber work, with 1,000 Mosquitoes worth of components built in their works by 1944. High Wycombe's long expertise with woodwork meant the region contributed significantly to Mosquito production. The furniture industry had created a concentrated workforce skilled in lamination, joinery, and precision woodworking. Cabinet makers, piano makers, coach builders, their skills transferred to aircraft production. De Havilland recruited from these trades, bringing non-strategic skilled labour from the furniture and allied industries into aircraft manufacture. But we should be careful about overstating this connection. The furniture industry workers built components. They applied skills developed in peacetime crafts to wartime production. Whether cabinet-making knowledge shaped the engineering choices at the drawing board level, or whether it simply enabled production once those choices were made, is a distinction the surviving record doesn't clarify. One source puts it plainly. The Mosquito wasn't built by furniture manufacturers. It was built by de Havilland. They employed craftsmen who had worked on fine furniture to make components. The design itself came from Bishop's team at Salisbury Hall. The initial Air Ministry response to de Havilland's wooden bomber concept was dismissive. In 1938, when Sir Geoffrey de Havilland first proposed a wooden high-speed bomber fast enough to dispense with defensive armament, the Ministry turned him down flat. "We outlined our scheme and showed the drawings," de Havilland later recalled. "They were barely glanced at. Then the bolder of the two officials addressed us like a schoolmaster." The Ministry favoured metal aircraft with defensive turrets, multiple crew members, conventional designs. They thought German fighters would be faster than expected. They wanted guns, forward firing, rear firing, turret mounted. A two-man, unarmed wooden bomber seemed impossible, impractical, irresponsible. Geoffrey de Havilland and his board believed otherwise. The company persevered with Mosquito development in secret, even after official rejection. When Lord Beaverbrook, as Minister of Aircraft Production, ordered concentration on 5 existing aircraft types during the Battle of Britain — Spitfire, Hurricane, Wellington, Whitley, Blenheim — Air Marshal Freeman didn't pass along the instruction to halt Mosquito work. The project that Beaverbrook had nicknamed Freeman's Folly survived because Freeman believed in it. By 1950, 7,791 Mosquitoes of all marks had been produced. The last, a night fighter, left de Havilland's Chester factory in November 1950, almost exactly 10 years after the prototype's first flight. All told, 3,326 Mosquitoes were built at Hatfield alone. The aircraft that officials dismissed as impossible became one of the most versatile and effective of the war. Fast bomber, night fighter, photo reconnaissance platform, maritime strike aircraft. The DH-91 Albatross airliner had pioneered the composite wood construction that made the Mosquito possible. That 22-passenger aircraft could cruise at 210 miles per hour at 11,000 feet, faster than the biplanes it was replacing. The wooden monocoque construction saved weight and compensated for the relatively low power of its engines. It simplified production and reduced construction time. The lessons learned on the Albatross, how to build fast, light and strong with wood, transferred directly to Bishop's speed bomber design. The knowledge that built both aircraft was scattered across drawing offices, factory floors and the minds of thousands of workers. Some of it was captured in manuals and specifications. The Forest Products Laboratory published detailed guidance on wood selection, glue mixing, clamping pressures. Strength values were tabulated for various species at specific moisture conditions and stress durations. Technical publications explained the behavior of shear stress along center faces under compression loading. But much of it was never documented. The decisions that seem most obvious are often the ones least likely to be written down, because to the people making them, no explanation was needed. A boat builder turned aircraft designer didn't need to write a memo explaining why he designed structures to put glue joints in shear rather than tension. He just did it. The way a cabinet maker doesn't explain why they orient grain a certain way in a load-bearing joint. The knowledge was embodied, tacit, passed from master to apprentice through demonstration rather than documentation. Tacit knowledge, what we know but often can't articulate, formed the foundation of much wartime engineering. Experience-based understanding, mostly undocumented, contained in the hands and eyes of craftsmen who knew when a joint was right by feel rather than measurement. The de Havilland tradition emphasized this kind of embodied expertise. The former de Havilland factory at Hatfield closed in 1993. Archives remain. Historians have combed the Hatfield archives for every Mosquito-related image and document. Family archives provide treasure troves of previously unseen photographs and diaries. Files at the National Archives contain correspondence about Mosquito acquisitions and production dating from 1943 and later. The RAF Museum holds records of aircraft designers, including de Havilland materials. Stephen Kipax's digitised archive of SOE contributed to recent historical work on Special Operations Mosquito missions. The BAE Systems Central Archives at Farnborough holds de Havilland records. It's possible design rationale documentation exists, but hasn't been accessed or recognised by researchers. But some significant elements of the story are genuinely absent from the historical record. The engineering rationale for specific design choices. The conversations between Bishop and his team about why this shape rather than that one. The prototype W4050 survives. You can see it at the de Havilland Aircraft Museum at Salisbury Hall, the very location where it was built in secrecy during the Battle of Britain. The wing is right there. You can trace the line of its leading edge from root to tip. See the shape that's launched 1,000 comments asking why. The wing shape wasn't strange aeronautical theory. It was consistent with woodshop logic, the kind of reasoning a boat builder or cabinet maker would understand without needing it explained. Laminated spars perform better when the loads favour directions where glue joints are strongest. Straight edges simplify manufacturing when you're building thousands of aircraft on compressed wartime schedules. Cross-lamination distributes stress across multiple grain orientations. The shape worked beautifully. The engineering decisions created an aircraft faster than almost anything else in the sky, versatile enough to serve as bomber, fighter, reconnaissance platform and transport. An unarmed wooden aircraft that outran the fighters sent to intercept it. But why exactly Bishop and his team chose this specific planform? The precise reasoning articulated in rooms at Salisbury Hall during the spring and summer of 1940 can't be definitively established. The museum that houses the prototype admits it. The documentation doesn't exist or hasn't survived. The people who could explain it died years ago, taking their knowledge with them. The commenter, whose father was on the design team at Salisbury Hall, might have gotten an answer if they'd asked while he was still alive. Maybe he knew. Maybe he was in the room when the geometry was debated. Maybe he absorbed the reasoning through years of working on the aircraft, understanding it the way a craftsman understands their tools, instinctively, wordlessly, obviously. 15 years too late to ask. If your father, grandfather, uncle or neighbour worked at de Havilland, at Salisbury Hall, at Hatfield, at F. Wrighton and Sons, or Dancer and Hearn, or any of the subcontractors who built the wooden wonder, leave a comment. The previous call for these stories generated the highest engagement of any comment on that video. People want to share. People want their family's contributions remembered. The fragments you remember might connect to fragments someone else remembers. The offhand comment your grandfather made about wood grain or glue joints, or why they did things a certain way, might be the missing piece that explains something historians have puzzled over for decades. What seems like casual family history to you might be the only surviving record of a conversation that happened in a drawing office in 1940. These stories are disappearing. Every year, more of the people who were there die, taking their knowledge with them. Even fragments help piece together what was never written down. What we know for certain: the Mosquito wing spars used laminated spruce flanges with birch plywood webs. Ash reinforced the high-stress areas. Casein glue held it together, applied under clamping pressures specified down to the PSI. Cross-lamination managed wood's anisotropic properties. The straight leading edge simplified manufacture. The shape worked. What remains mystery? The exact words R.E. Bishop spoke when deciding on the geometry. The specific moments when this shape was chosen over alternatives. The tacit knowledge that made certain choices obvious to men trained in wood, but invisible to historians trained in documents. The people who could have explained it are gone. What survives is the wing itself, the engineering logic that makes sense of its shape, and the fragments that families still remember. Subscribe for more stories like this. And if you have any connection to de Havilland, any memory of what someone told you about building the wooden wonder, leave it in the comments. Your family's knowledge might be the closest we'll ever get to answers.